Dew point is the temperature at which air must be cooled to reach 100% relative humidity. When air comes in contact with a surface that is below the dew point, water vapor in the air will condense on the cold surface. We've all experienced this when drinking an ice-cold beverage. This can be problematic for air cooling evaporators that operate below the freezing point of water. As air passes through the finned surface, water vapor will freeze on the surface of the coil. This frost decreases the evaporator capacity for two reasons. First, it reduces the distance between fins, which restricts airflow. Less airflow results in less heat transfer. Second, the frost acts as an insulator, which negatively impacts the heat transfer capability of the evaporator. Because of this phenomenon, in most situations, air cooling evaporators must be periodically defrosted. There are four primary defrost methods employed in industrial refrigeration systems: air defrost, electric defrost, water defrost, hot gas defrost. Air defrost is the simplest form of defrost and is achieved by shutting the evaporator off for a long enough period of time that all frost melts from the coil. This method takes a lot of time and therefore requires the room temperature where the evaporator is located to be raised to allow melting to occur. For this reason, air defrost is rarely employed. Electric defrost consists of tracing the tubes and pan with electric heaters that, when activated, will cause the frost to melt and collect in the drain pan. This method is commonly used in halocarbon systems. Water defrost is accomplished by spraying ambient temperature water over the surface of the coil, which causes any ice to melt. When water defrost is used, it is important that the coil be allowed to drip for an extended period of time after defrost, before turning the evaporator back on. If the evaporator is turned on too soon, water on the surface of the coil may freeze, rendering the defrost pointless. Hot gas defrost is the most common defrost technique used. In hot gas defrost, the evaporator is piped so that high-pressure refrigerant vapor can pass through the evaporator, causing the frost to melt. One way to think about hot gas defrost is that the evaporator becomes a condenser during the defrost cycle. Instead of absorbing heat, the evaporator will reject heat from the warm vapor, which causes the frost to melt. The downside of hot gas defrost is that it requires additional piping, valves, and controls as part of the system design.
In this video, I just want to walk through what valve groups might look like for a recirculated system using ammonia refrigeration. Obviously, every system is unique and it won't be exactly like this, but this is somewhat typical to give an overview. First of all, we got a lot going on here. This is piping going to a single evaporator inside a penthouse, and mainly there's four different pipes. This first one we call the defrost condensate. This is our recirculated liquid. Now this particular evaporator is called a convertible evaporator because it can be connected to the high temperature liquid or the low temperature liquid. So that adds a little bit of complexity, but only one of those is open at any given time. So this is the liquid valve group, and this is a block valve. So we've got all contained within the single block. We have an isolation valve, a strainer, a solenoid, a hand expansion valve, that's the yellow handle, and another isolation valve. There's also a check valve component within this as well. It's frosted over, so it's kind of difficult to see. Moving on, behind that is the hot gas solenoid valve, and this is an advanced form of hot gas valve that has the two solenoids you see there, because it's got two stages of it. The preheat stage, it opens at about 10%, and then the second stage, which will be fully open. All right, and then the big valve there, that's the suction stop valve. So, and again, it has a couple solenoid components too for various stages that it could be open. Now, under normal conditions, liquid will be flowing through this solenoid valve based on the temperature in the room. Liquid goes into the evaporator, the fans pull air over it, causing that liquid to boil. It exits through the suction pipe labeled LTRS through the suction stop valve into the main, which takes it back to the recirculator in the machine room. Okay, when we go to hot gas defrost, the first thing that will happen is this valve will shut off. The fans turn on and continue to run while it goes through a pump down period of, let's say, 10 to 15 minutes, depending on the coil and how the system's set up. Then the hot gas solenoid is ready to activate. And again, I said this is a 2-stage solenoid. So the first stage, when it activates, only opens the valve about 10%. That might be called a preheat stage. We're letting some hot gas into the coil, but it's not at its full flow yet. At the same time, this suction stop valve, due to the gas getting added to it, will close. So it is no longer open. There's no more gas passing through this way. Inside the room, we can't see here, but that goes in there. That pipe enters the room and then it flows through the coil backwards. So it's flowing, instead of going through the liquid, it's going through the suction pipe and exiting through this liquid pipe. But because of the check valve in here, it can't go this direction, and it's forced now through this route here. And this is our defrost condensate regulator, which has a set point of 70 or 75 psi. So once that pressure starts building in the coil, we'll hear the flow through this regulator, which terminates into the high temperature suction main. Again, that goes back to the machine room. So there's a lot going on here. It can be intimidating, but if you kind of just stop and look at each branch and what it does, it really does make sense.
To avoid the room temperature deviating too high during defrost, most systems are arranged so that the evaporators can be independently defrosted. Coils will alternate through a defrost to avoid significant changes in the room temperature. Air cooling evaporators will have a pan to collect water that drips from the surface during defrost. The drain pan is also susceptible to freezing, so it must be accounted for in the defrost system. When hot gas defrost is employed, the drain pan will typically have tubes piped through it. Warm ammonia vapor will pass through the pan before entering the evaporator. Water that collects in the pan will freely drain through the defrost condensate drain pipe. All drain lines must be trapped. If the room operates below freezing, the drain pipe must have a heat trace to prevent water from freezing in the drain pipe.